Gravity may explain why the universe can create life without breaking the laws of physics. Source: Queen Mary University of London research published in Physical Review. For nearly 2 centuries, one of the most fundamental laws of physics has appeared to tell a simple story about the fate of the universe. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Entropy is often described as a measure of disorder, although physicists define it more precisely as the number of possible ways energy and information can be arranged. Imagine a perfectly organized room. If nobody cleans it, it gradually becomes messy. Books are left on tables, clothes pile up, and objects become scattered. The room naturally moves toward disorder, not greater organization. This simple observation reflects one of the deepest principles governing the physical universe. From melting ice cubes to burning stars, nature consistently moves toward increasing entropy. Albert Einstein himself regarded the second law as one of the most secure principles in all of science, famously describing it as holding a unique position among the laws of nature. Yet when we look around the cosmos, something doesn't seem to fit. If everything naturally becomes more disordered over time, why does the universe appear to become increasingly organized? Over billions of years, simple clouds of hydrogen evolved into galaxies, stars, planets, oceans, living organisms, and eventually intelligent beings capable of questioning the very laws that govern their existence. Rather than descending into featureless chaos, the universe seems to have built layer upon layer of astonishing complexity. This apparent contradiction has puzzled physicists for decades. How can complexity continue to grow if entropy is always increasing? Does life somehow violate one of the most fundamental laws of physics? Or have we been missing an important piece of the puzzle all along? A fascinating new theoretical study from Queen Mary University of London now offers a possible answer. Mathematician Professor Ginstra Bianconi has developed a new framework suggesting that the universe can indeed become more complex while fully obeying the second law of thermodynamics. The key idea is surprisingly simple, yet profoundly different from how entropy is usually imagined. Instead of focusing only on the total amount of entropy in the universe, the theory distinguishes between total entropy and the amount of entropy contained within each unit of space. According to the new calculations, as the universe expands, its total entropy continues to increase exactly as thermodynamics requires. However, because space itself is constantly growing, that entropy becomes spread across an ever larger volume. As a result, the entropy contained within each local region gradually decreases. In other words, although the universe contains more total entropy than ever before, each individual portion of space may actually become more ordered over time. Those local pockets of reduced entropy could provide the conditions needed for matter to organize into galaxies, stars, planets, and ultimately life itself. Rather than violating thermodynamics, complexity may emerge precisely because the expansion of space redistributes entropy throughout the cosmos. To understand why this idea is so significant, we first need to explore what physicists actually mean by entropy. Popular science often describes entropy simply as disorder, but the concept is much richer than that. Entropy measures how many microscopic arrangements are possible while still producing the same overall physical state. Consider a deck of playing cards. A brand new deck arranged perfectly by suit represents only one highly ordered arrangement. Shuffle the deck thoroughly, and there are an almost unimaginable number of possible arrangements that all appear equally random. Because there are vastly more disordered arrangements than ordered ones, systems naturally evolve toward higher entropy. The same principle applies throughout nature. A hot cup of coffee left on a table cools because the heat spreads into the surrounding air. Gas released inside a room spreads evenly rather than remaining concentrated in one corner. Energy continually disperses, making highly organized states statistically less likely over time. From this perspective, the emergence of complex structures such as galaxies or living cells appears deeply puzzling. These systems are extraordinarily organized. They require matter and energy to arrange themselves into remarkably specific configurations that seem far less probable than random disorder. For decades, physicists have understood that local decreases in entropy are allowed, provided they are accompanied by even larger increases elsewhere. Living organisms, for example, maintain internal order by consuming energy from their surroundings. Yet, explaining how the entire universe simultaneously produces increasing complexity while total entropy continues to rise has remained one of cosmology's deepest unanswered questions. Professor Bianconi approaches this mystery using an emerging theoretical framework known as gravity from entropy, often abbreviated as GFE. Unlike Einstein's general relativity, which describes gravity as the curvature of spacetime produced by matter and energy, gravity from entropy proposes that gravity itself may emerge from something even more fundamental. According to this idea, spacetime possesses microscopic quantum properties that behave similarly to the countless particles making up a gas. Just as temperature emerges from the collective motion of molecules, gravity may emerge from the statistical behavior of spacetime's microscopic building blocks. In this picture, gravity is not simply a fundamental force, but an informational phenomenon intimately connected to entropy. The theory draws heavily on statistical mechanics, the branch of physics that explains how large-scale properties emerge from enormous numbers of microscopic interactions. If correct, gravity would become deeply linked not only to geometry, but also to information, thermodynamics, and quantum mechanics. Such a connection could help bridge one of modern physics' greatest challenges, reconciling Einstein's theory of gravity with quantum theory. Interestingly, the idea that gravity and thermodynamics might be connected is not entirely new. During the 1970s, physicists Jacob Bekenstein and Stephen Hawking revolutionized our understanding of black holes. Before their work, black holes were thought to be perfectly black objects from which nothing could escape. Bekenstein proposed that black holes possess entropy proportional to the area of their event horizons, suggesting they contain hidden microscopic information. Hawking then demonstrated that black holes are not completely black after all. Through quantum effects near the event horizon, they slowly emit radiation and gradually lose mass. These discoveries revealed a profound relationship between gravity, temperature, entropy, and information that continues to shape modern theoretical physics. Gravity from entropy builds upon these insights by extending the thermodynamic description beyond black holes to spacetime itself. Rather than treating entropy as something associated only with extreme objects, the theory suggests that the very fabric of the universe possesses thermodynamic properties capable of giving rise to gravity. Using this framework, Professor Bianconi analyzed mathematical models describing an expanding universe known as Friedmann-Robertson-Walker spacetimes, which cosmologists commonly use to describe the large-scale evolution of the cosmos. The calculations produced an intriguing result. As expected, the universe's total entropy increases continuously as space expands. But because the volume of the universe grows even faster, the amount of entropy contained within each unit of space gradually decreases. Imagine pouring a fixed amount of ink into a balloon. As the balloon inflates, the total amount of ink remains unchanged, yet each small region contains less and less ink because it has become spread over a much larger volume. The theory predicts a similar process for entropy. Expansion doesn't eliminate entropy. Instead, it dilutes it across an ever-growing cosmos. Those locally lower entropy environments could provide ideal conditions for gravity to gather matter into galaxies, stars, planetary systems, and eventually biological organisms. Complexity becomes possible not despite increasing entropy, but because cosmic expansion continually redistributes it. The model also introduces an intriguing connection to one of cosmology's greatest mysteries, dark energy. Observations over the past quarter century have shown that the expansion of the universe is accelerating rather than slowing down. To explain this unexpected acceleration, cosmologists propose the existence of dark energy, an unknown form of energy that appears to fill empty space and drive cosmic expansion. Despite accounting for roughly 70% of the universe's total energy content, its true nature remains completely unknown. In Gravity from Entropy, however, a dark energy-like contribution arises naturally from the theory's mathematical framework. Under ordinary conditions, the equations closely reproduce Einstein's general relativity. But, under more extreme circumstances, additional terms appear that behave similarly to evolving dark energy. Unlike the cosmological constant traditionally inserted into Einstein's equations, this version changes dynamically as the universe evolves. That means future astronomical observations could potentially test whether these predictions match reality, providing one possible experimental path toward evaluating the theory. Although these ideas remain highly theoretical, they carry profound philosophical implications. They suggest that the emergence of complexity, life, and perhaps even intelligence may not represent improbable exceptions to the laws of thermodynamics. Instead, complexity could be a natural consequence of an expanding universe whose entropy becomes increasingly distributed across space. Galaxies, stars, planets, ecosystems, and civilizations would not stand in opposition to entropy, but would emerge within regions where local conditions temporarily favor increasing organization. In this view, cosmic expansion doesn't simply make the universe larger. It continuously creates new opportunities for structure to arise, while remaining fully consistent with thermodynamic principles. Of course, the work is still in its earliest stages. Gravity from Entropy has not yet replaced Einstein's theory, nor has it been experimentally confirmed. Many predictions remain to be tested, and physicists continue searching for observational evidence that could distinguish it from existing models. Yet history has shown that some of the greatest scientific revolutions begin with bold theoretical ideas capable of explaining long-standing mysteries from an entirely new perspective. Whether this framework ultimately proves correct or inspires an even deeper theory, it represents another important step toward answering one of science's oldest questions. Why does a universe governed by increasing entropy continue, producing astonishing complexity? If future research supports these ideas, the answer may be remarkably elegant. The universe doesn't create order by breaking the second law of thermodynamics. It creates order because the expansion of space itself continually reshapes how entropy is distributed. Total entropy keeps rising, exactly as physics predicts. But locally, the cosmos gains room for galaxies to assemble, stars to ignite, planets to form, chemistry to flourish, and life to emerge. In the end, the same expanding universe that seems destined for increasing disorder may also be the very reason complexity, and perhaps our own existence, became possible in the first place.